This is section 8.8, second half of that on page 2. We're still talking about geometric sequences and exponential functions. We have compound interest with a second scenario. On page 1 we talked about compounding annually. Now we're compounding quarterly. That's 4 times per year. Now that's going to influence what our percentage rate is, as well as the number of times that the interest compounds. One will be dividing by it and one will be multiplying it by it. Now we have to say, if we have 7.2% annually, what is that on a quarterly basis? Well, let's take 7.2 and let's divide that by 4. So what we have is 7.2 divided by 4. So it's 1.8% compounded quarterly. What does that equal? 101.8%. Now, as a percentage then, we convert that to a decimal. Our multiplier, or our B factor, our growth factor, is 1.018 every quarter. That's every 3 months. With that in mind, we're also going to have to figure out how many times the interest compounds. We're still going for 5 years, but it's 5 years times 4 times per year, or 20 as an amount. So here's our equation. Y equals our initial amount, once again 1,000, times our growth factor, 1.018, raised to the number of times that we're going to be working this through, which is 20 and not 4 or 5 as we had before. So as we put this in, we have to make sure that we're going to raise our powers to the correct amounts. So let's take 1,000 times 1.018 and raise that to the 20th power. As you can see, we get $1,428.75 as our amount. As we compare this to the previous page, as you look back, if you'll notice, this amount is different than what we had before. Now, because we compounded our money quarterly, we have a larger amount because we're getting interest on the interest of each quarter. So that is our problem as we compound quarterly. It's a lot different as you compare quarterly or annually. Had this been done on a monthly basis, we could also compare it in that capacity. What I'd like to do very briefly, if you just work with me, let's take a look at the same problem, except now let's compound it monthly. What is going to change? I think compoundly is a new word. So if we compound this monthly, now our growth factor is going to be 100% plus 7.2 divided by 12%. As we work through this, 7.2 divided by 12 is 0.6. So we have 100% plus 0.6%. That's 100.6%. As a decimal, 100.006. That is our growth factor. However, the number of times that the interest compounds, in this case, will now be a lot different. It's still for 5 years, but we're going to multiply that by 12 times per year. So our growth factor is 60. So here's our new equation. Y equals our initial amount, 1,000, times 1.006 raised to the 60th power. If you were trying to estimate this, would you say it's more or less than compounding quarterly? Well, let's take a look. 1,000 times 1.006 raised to the 60. $1,431.79. So in this case, it actually is more than our actual amount that we had compounded quarterly. It's just a showing that as you compound more and more over the course of a year, you'll get more and more interest compounding on itself. So just an example of compounding monthly, compounding quarterly, or on the previous page, compounding annually. Now we look at half-life as our fourth example for this lesson. Half-life, we have a certain synthetic substance that was developed here at the school called warium. And warium has a half-life of 6 hours. This is something that's often developed in chemistry class by the advanced chemistry students when they're doing electrostatic charge and testing. So, suppose we have a lab with 80 milligrams of this warium, and the students link hands in such a way that the warium is conducted down the way, and it shocks people if you touch it in a too strong a manner. Now all that is peripheral knowledge, but we have to focus on the idea of the 80 milligrams of warium. Well, if the half-life is 6 hours, after 24 hours we have to say how many half-lives have we had. Well, in that case, X would be 4 times. Since it's a half-life, our growth factor is 1/2. So our equation is going to look like this: 80 milligrams times 1/2 raised to the 4. Well, you know it by this point that 1/2 times itself 4 times is 1/16. And so we merely take 80 and we divide it by 16. So what is the half-life? And the amount left? Well, there'll be 5 milligrams left after 24 hours. Just as easily, we could say after 48 hours, X is then no longer 4 times. Now X, how many times is 6-hour time spans go into 48 hours? Well, X is 8 times. So this is 8 half-lives. So now we say 80 times 1/2 raised to the 8th. As the numbers start to get a little bit difficult, we can merely do this on our calculator. 80 times parentheses 1 divided by 2 close parentheses raised to the 8th power. How much is left after 48 hours? Well, as you can see, Y will now equal 0.3125 milligrams. Certainly after 2 days, this warium has gone from 80 milligrams down to less than 3/10 of a milligram. That's a good example of half-life. Half-life meaning your multiplier is 1/2, and then you have to determine how many times you're going to have that half-life cycle. Our last illustration just is very simply to try to identify the difference between growth and decay. If we have a growth factor for an exponential function, if we review and think back to what we have on the first page, if the factor of the multiplier b is greater than 1, it will be growth. If it's less than 1, it will be decay. So very simply what we need to do is we need to analyze our equations and compare them back to our standard equation. Remember, A is the initial amount and B is the growth factor or the decay factor. So let's circle our decay factor on this first one. The decay factor is 0.5. Obviously that's less than 1. So B is less than 1. So this is an example of decay. Here our second one, once again, our factor, our multiplier is 2. Well, here B is greater than 1. So that's an example of growth. What's it going to be for here? Is it 2? Is it 3? Actually, it's 2/3. Well, obviously 2/3 is less than 1, so that's an example of decay. Look at our last one. What's that going to be? 5/6 is the initial amount, very small you may say, but the growth factor is actually 1.02. And since 1.02 is greater than 1, that's an example of growth. Each one of these is an example that we could have in a real story problem. This first one, just for a comment of sake, if you notice the factor is 0.5, that's 1/2. That could have been a problem that we talked about half-life, because half-life means the growth or the multiplying factor is 1/2.